Hello student, so in this lab session we are going to see DSB modulated signal, dual sideband modulated signal. So already you know that it is a form of amplitude modulation, and here we are going to use the balance modulator implementation to get the DSB output. So you already know that in AM amplitude modulation, in conventional AM modulation, we will have the carrier signals with the modulated signal, no? But that carrier signal doesn't have any information signals. Okay, so if we are sending the total spectrum, total signal, that we need more power to transmit the signal, because that carrier signals has very large power in it. Okay, so it is a waste of power. So we are using this so-called DSB modulation, dual sideband modulation. In that modulation, we just remove that carrier frequency component, okay, and send only to sideband, so that we can reduce the transmission power. Okay, so we will see how we can see it. So for this lab session also we are going to use modulator board, modulator demodulator board, but we are going to demonstrate only the modulation part, not the demodulation part. So so here you can see in DSB dual sideband suppressed carrier modulator, there should be two amplitude modulator, no? One we are giving direct carrier signal, okay, and for other modulator we are giving 90 phase shift carrier signal. Then we get the output of that two modulator and send it through a summer. That means we will add those modulated signal together and we can get a DSB output. Okay, so we have learned this in our in the classroom. So we will see the waveform and the spectrum. Okay, so here we have the modulating signal generator. Okay, so if we see the modulating signal, so you can see that. So I am going to connect the ground. Okay, so I am going to see the waveform, okay, time domain signal through the oscilloscope, okay, through our digital oscilloscope, digital storage oscilloscope. So you can see that we have a sine wave as our information signal. So this is also a single tone modulator. Okay, we are going to demonstrate the single tone modulation here. So you can see that the information signal frequency is about 4.4 kilohertz. Okay, 4.4 kilohertz. Okay, and you can see you can change the amplitude here. Okay, you can change the amplitude here. So you can see maximum amplitude we can get 5.6 and minus 5.6. That means peak to peak about 12 volt. No, okay. This is our information signal parameter. And if you want to see our carrier signal, okay, carrier signal. So you can see this is our carrier signal, okay, and the frequency is about 91 kilohertz. Okay, 91 kilohertz. Modulating signal is about 4 kilohertz, no, 5 kilohertz, maybe 5 kilohertz. So if I see the so here carrier signal generator will generate two carrier signal here. One is zero phase carrier signal, and that should be given to one AM modulator, Another is 90 phase shifted carrier waveform, carrier signal, and it should be given to other balance modulator. Okay. So, here I am going to see my other signal also, the 90 phase shifted carrier signal also, and you can see it is about 90 kilohertz, 91 kilohertz, and same peak to peak value is there. Okay. So, if you want to see the spectrum of this sinusoidal carrier signal, you can see it through our spectrum analyzer. Okay. The output of the carrier signal. So, we have a sinusoidal RF signal. Okay. So, you can see that we can see one peak here. Okay. So, here it is about 91, no, 91.3.6, and we can get the power level here. Okay. The peak power level here, and if you reduce the amplitude, okay, amplitude of that signal, so you can see that the power also reducing, and when we are increasing the amplitude, then that peak is increasing. Okay. So, we have already seen these things in our AM modulator. Okay. So, now I am going to do the modulation. Okay. So, you can see that here I have the modulating signal. Okay. So, I am going to connect it. So, this is my information signal. Okay. So, this is my information signal, 4 kilohertz sine wave. Okay. So, I am going to connect it to one modulator. So, here we have two modulators. Okay. AM modulators. Okay. This is first one and this is second one. So, I am going to connect my information signal to first amplitude modulator and my the carrier signal into other. So, here I have connected the 90 phase shift carrier signal. Okay. 90 phase shifted carrier signal I have connected to this balance modulator. Okay. So, if I see the output of that modulator, okay, if I see the output of that modulator, so this is oscilloscope. Okay. So, you can see this is the oscilloscope. Now, I am going to check that waveform through the oscilloscope. Okay. So, you can see some distorted value there. Okay. So, I am going to increase my carrier signals. Okay. Okay, you can see that. Okay, we have a signal, no? Okay, but what is the issue here? You can see that one, if I get single shot, okay, you can see that the minimum point cross the zero level, no? This is the zero level, zero line, and the minimum level cross that point. So, this means over modulation, no? Okay. So, here we got over modulation scenario. Okay. So, we can change the amplitude, the modulation index to mitigate that effect. Okay, so, I am going to reduce my. So, you can see that when I am reducing my information signal amplitude, okay, you can see that that effect is reducing, no? So, you can see that my effect is reducing. When I am increasing the amplitude of my information signal, so that you can see that the over modulation effect is increasing. Now, I am increasing the amplitude of message signal. So, over modulation is increasing. Okay. And when I decrease it, okay, when I decrease the modulating signal, information signal amplitude. So, you can see that now it is not over modulated, no. Now, it is near to 100% modulation. Okay. If I, that means my carrier amplitude and modulating amplitude is same, no, in 100% modulation. Okay. So, I'm going to change it more. Okay. Sorry. Okay. So, I am going to change it more. Now, it is about 100 modulation. So, I am going to reduce the amplitude of my information signal more. Now, you can see that now it is reducing the modulation percentage, no. Okay. You can see that. Okay. Okay. So, I think this is okay, no, this modulation is okay. So, this is somewhat okay. It may be about 50 modulation or something. Okay. So, so you can see the amplitude modulated signal here. Okay. So, if we see the spectrum, okay. So, I am going to, so we have seen the waveform. If we are going to see the spectrum, okay. So, I am going to see the spectrum of this signal. Okay. Okay. You can see, no, you can see the spectrum. Okay. Okay. Look at the spectrum analyzer. Now, I am going to connect that modulated output, amplitude modulated output to our spectrum analyzer. So, you can see to one peak, one carrier peak, and this two side bands. Okay. So, this is our carrier signals and this is our side band, okay, which is created from our message signal. Okay. So, this should be Fc minus Fm, this should be Fc plus Fm, and this is Fc. Okay. So, the spectrum is okay. So, we will see okay. So, one modulator is okay, the other modulator also will give us the same result. Okay. So, I am going to connect the message signal and carrier signals to other modulator also. Okay. So, here we have 0 phase shifted carrier signal, and I have connected to one modulator. Okay. And I have my message signal. Okay. That is also 90% shifted signal, and I have connected to my other modulator. Okay. So, this is one amplitude modulator and this is another amplitude modulator. Okay. So, I am going to add this signal together. So, I am going to give that signal to a summer adder. Okay. So, this is my adder circuit. Okay. Then here I will get DSB signal, no, dual sideband signal. Okay. So, you can see it. Okay. So, if you see the waveform first, So I hope this signal is okay, no? Okay, I hope this signal is okay. So this is kind of a dual sideband modulated signal. So you can see the waveform in MATLAB also. We have seen it, no? We have, when in our classroom, when we were in our classroom, we have seen this waveform in MATLAB. We have generated this waveform using MATLAB and C. Okay. So I hope this signal is somewhat okay, and you can see that by changing the carrier frequency and amplitude, we can somehow get proper modulated signal. Okay. Okay, anyway, to continue our discussion, I hope this waveform is okay. So you can see that this is a modulated signal. Okay, we can see the envelope there. Okay, and no, okay. So you can see that this is somewhat okay, no? And if I so I hope this okay, this one okay. Okay, so this is our modulated signal. Okay, so we will check the most important thing is the spectrum of the signal. Okay, so we will check the spectrum. Okay, so I connect my signal. Okay, I connect my signal, my output modulated signal to the spectrum. Okay, you can see one peak, no? So I hope this is our spectrum. Okay, okay, I hope this is our spectrum. Okay, and you can see that here carrier is not totally suppressed. Okay, so we have some carrier power, carrier peak, and but it is suppressed. No, in modulated signal you can see that this is somewhat high, the peak is high. Okay, but here up to some level it is suppressed, but it is not totally suppressed. Okay, actually that's happened due to the unreliable of these connections and the component we are using. So anyhow you can get idea here. Okay, so you can see that the carrier peak is very low. Okay, carrier peak is very low, and we will get two sidebands only. Okay, so this is actually DSB modulation, dual sideband suppressed carrier modulation. We have implemented this modulator through to a modulator. We called it balance modulator. So I think you get the idea how we can suppress the carrier signal and why we are going to suppress it, and the spectrum, how the spectrum look likes in this case. Okay.